Welcome to EE555 discussion on Wednesday, April 23rd, 2014.
Okay, good morning, everybody. Today we'll talk about two problems on optical networks. First of all, I have to say that this is the last discussion, officially. Next week, I will be available during the discussion times in my regular office hours in PHE 330. And if you have questions, you can come and talk to me or Nachi after my office hours about the topics basically for the term paper, or if you have other questions about discussions and homeworks, okay? And of course, we'll have more office hours before the exam, but just, the regular discussion times will be office hours as well. Okay, so let's get started. Let's see the first problem. We have consider a 5-node unidirectional optical ring network. A SONET OC192 framing structure over single wavelength is used between adjacent nodes in the ring. There is a SONET ADM and a router attached to each node. There are two options for configuring the network. The first option is the virtual topology is bidirectional 5-node ring. So there are 10 circuits in total. And the second option is the virtual topology is a fully connected mesh. I.e., a dedicated circuit is provisioned between each source and destination. Okay, so we have a total of 20 circuits in this case. We'll see why a mesh of 5 is 20, but so that's the second. Now, question A anyway. If all circuits have the same capacity and assuming all partitioning of OC192 is possible, what is the maximum capacity that can be assigned to circuits in its design? So the first thing we need to find is the maximum capacity. Okay. The second is, given the assignment in part A and assuming a uniform traffic matrix, find the network average delay for the two networks. Plot your results as a function of the total network traffic gamma, or the external traffic, right? Okay, do we understand the question? So we have a 5-node unidirectional optical network ring, SONET OC192 framing structure between adjacent nodes in the ring, and we have two virtual topologies. We want to support two virtual topologies. For us, those are two different problems, right? Part A and part B. And we want to find, for both cases, maximum capacity and network average delay. That's all. All right, let's see. First of all, how is the physical topology? How does it look like? Oops, problem number 1. Physical topology is a physical topology of 5 nodes, and it's unidirectional. So we have a let's do it this way. E. All right. Okay, that's the physical topology. Why is that? Because it's a 5-node unidirectional, okay, optical ring network. Now, how is using this? How can we build on top of that what is given in part A, a virtual topology, which is bidirectional 5-node ring with 10 circuits. Just to put some notation over here, we will call these edges over here segments, right, in the physical topology. So we have of 5 segments. Why I'm putting this down? Because it's important when we define quantities later to know exactly what we define and in which topology. Now, the virtual topology A, virtual topology is going to look like what? We have 5 nodes again. So A, any ideas how it's going to look like? We want to support, where is that? A bidirectional 5-node ring. You should be familiar with that, familiar in the sense that you should be able to do this physical to virtual mapping, okay? Depending on what is the question. So in this case, if we want to support, let's say, a connection between A and B, we will use the underlying physical topology, just one hop, that's fine, right? So we can do this. We want also to support this kind of connection. Why? Because the virtual topology, it's a requirement that it should look like this. It's a bidirectional 5-node ring. Bidirectional 5-node ring is going to look obviously like this. Let me draw it first and then we'll talk how is it. I messed it up, the up and down, but you see what I mean. We're supposed to have one, the same direction. Okay. Do you agree with that? Now, how is that possible over this physical network? Topology A. To achieve this over this, for example, if you want to connect A and B, you just go this way. If you want to connect B and A, you have to go all the way around. All right? So we have, for the one arrow, one direction, we have a hop of 1. For the second direction, we have a hop of 4. Make sense? Okay. So let's keep that in mind when we calculate average path length and stuff like that. All right, good. Now, let me just put a note over here to achieve the reverse direction, or e.g. B to A, we need 4 hops in the physical topology. Okay? Just to make it clear. Now, we will call this a circuit. Make sense? So over here, the total number of circuits in the virtual topology is 10. So we have 2 quantities so far, total number of segments, and total number of circuits in virtual and logic, in physical. Okay, perfect. Now, what do we want from here? We want to find The maximum, where is that? The maximum capacity that can be assigned to circuits in its design. In other words, we want to find how much is the bandwidth in each circuit over here. And why we are asked this question, because to support this kind of connectivity, it feels like we are wasting bandwidth going back and forth to support this bidirectional. And the more the nodes are to the right and they want to connect to the left, the more the traffic is going to be carried through a circuit. Okay? So we expect to find a value less than OC192, which is the capacity of the ring over here. That's what we're trying to do. Okay. Now, let's continue our analysis. To find what I just said, we want to find what? How many circuits we have per segment. How many circuits per segment, in order to see how many people are sharing the OC192. Do you agree? Okay. Let's go calculate those things. So we have total number of circuits, as we said, 10. Average circuit length, on logical topology, measured in segments of the physical topology, is equal to average circuit length, okay? We want to find, do you understand what I'm trying to find over here? We have 10 circuits. We said that. How many segments is on average a given circuit? So what do we want to average over? The 10 circuits are 1, 2, 3, 4, 5, and then the reverse. That's clear. So we expect that we should add the segment length of each circuit and divide by 10, which is the total number of circuits. Now, the segment length of the circuit of this A to B circuit is 1. One segment, they are directly connected. The segment length of B to A is 4. You have to go all the way. Oops. You have to go all the way down. Do you agree? We're counting it in segments. Make sense? So A to B, B to C, C to D, blah, blah, blah. This is 1 in segments. The reverse, all of them are 4. Because in the physical topology, you have to go all the way down to achieve the virtual reverse path. Make sense? All right, so that's what we will say over here. So this is 1 plus 1 plus 1 plus 1 plus 1 plus 4. Five, and this gives over 10, 5 over 2. Do we all agree? Okay. Now, another metric that we want is to find the number of circuits per segment. Why we want that? Because that's what is going to give us how many people are sharing the bandwidth. How many people are sharing the bandwidth of OC192? So we want to find the circuits per segment is equal to what? 2 over 5. Let's see. We have 10 circuits and we want to in the denominator to add the total number of segments, or that corresponds to these 10 circuits, or in other words, we can have total number of circuits times average circuit length in segments over 5 segments. And this gives 10 times 5 over 2 over 5 gives 5 circuits per segment. Do you agree? So in this case over here, we just found for this, each of those guys, how many people are passing through? How many circuits? How many circuits we want to support? Okay? Now, the next thing is to find the maximum capacity, which is the question, what the question is asking. All right? Maximum capacity equals OC 192 per circuit over here. It's important to put circuit or segment because we're talking about two different things. So just to make things clear, OC 192 divided by number of circuits per segment, divided by 5, which is the and this is equal to OC 38. The problem says that we support all the divisions of OC 92, assuming. So that's the capacity supported. Do you agree so far? Is clear? Okay. So that was for part A, and we want to do the same for part B, which is the delay. The second question over here is asking for, given the assignment in A and assuming uniform traffic matrix, find the network average delay for the two networks and plot your results. So I want to calculate the network average delay. So what we will talk about right now is very important. It might be in the exam, so just make sure you understand, okay? So average delay, how do you calculate average delay in general? Do you remember from network of queues? Anything network of, you should take a look in the presentation that says flows or network flows, I think. That's a small presentation that the professor gave where it has a lot of formulas on that. It's basically network of queues. Okay, so we'll use this kind of formulation over here too. First of all, let's calculate. For that, we need to calculate what? We want to calculate delay. So we need imagine we use Little's law. What does Little's law do? It relates delay with queue length and arrival rate. Do you agree? We'll use a similar approach here. We have a network of queues. In the case of network of queues, the same thing applies. So we have the total delay being 1 over lambda or gamma or your external arrivals times the average queue length. Inside, and actually queue length is not the right word is the average number of customers in each system, because we want to sum those guys and find the total number of customers in the system. Okay? So that's the formula for the delay. Now, to find how many customers we have in each system, we need to find how many hops, what is the average hop count, as we did in the previous discussion, if you remember. Average hop count, and then we found how many customers on average there are in customers, anyway, packets there in the system. Let's do that. Average path length in logical topology or in virtual topology in router hops in virtual topology, I'm repeating that, is now what? We want to find the average number of hops over here. You remember how we did last time? We just pick, first of all, it's symmetric. It's going to be the same for all the nodes. We stick to a node. We pick a random destination. What is the, I mean, we need to average out over all these random destinations, obviously. But if we, let's say the destination is this, what is the hop, number of hops? 2. If it's this, if it's D, from A to D, it's 2. Okay, so the total, we will do that for all the possible nodes, right? We start from one node, we have 4 possible destinations. So the average number of paths will be 2 plus 2 plus 1 plus 1 over 4. And this is equal to 3 over 2 hops. Okay. So you remember how we do that from the previous time. And now let's find the number of flows that pass from a circuit. And why we need that? We need that because the number of flows that pass through the circuit will be correlated, basically it's our internal arrival rate lambda or gamma I or whatever you want to call it, okay? For each system, the number of flows that move inside the network is going to be our, you remember when we were doing network of queues? We're talking about lambda I, the internal inside the network, and we had the external, the gamma or lambda without an index. That's what it is now, okay? So let's calculate that. The number of flows per circuit is equal to...
The time is 6 o'clock.
Total flows over total circuits. And this is equal to what? You remember this formula for the total number of flows, which relates the path length with the external arrival rate? We multiply the external arrival rate or external flow, or whatever you want to call it, times average path length, which is 3 over 2. And this would be divided by 10. And this is equal to gamma times 3 over 2 divided by 10, 3 gamma over 20. Make sense? Okay. Now, what else do we need? Now we can go ahead and calculate the delay. So for the delay, let's go to the next page. Delay equals expected T usually, or in other books you might see it as W. And as W, we represent an expectation. It's not a random variable, it's an expectation, okay? This is an expectation. T is the random variable here. What is that? As I told you, in the case of network of queues, we had, think about Little's law. How you find the delay based on Little's law? You remember the formula? Isn't it L capital over L lowercase over lambda? Huh? One notation. If you don't remember this notation, use whatever notation you want, but it's the length over the arrival rate. And that gives you the average delay. Same thing here in the network of queues. We need a formula for the average length, and we divide with gamma. All right, so it's going to be 1 over gamma times, let's call it, how we should call that? Let's call it average number of customers in the system, and this is equal to 1 over gamma summation over logical links in the logical topology of lambda ij. Lambda ij is internal rates. This is network of flows, right? That type of notation. The mu ij minus lambda ij. Now, if I give you this, that's a generic formula. We haven't defined these quantities, obviously, but we will do that just by plugging it in the right values now. Do you agree? I hope you didn't get lost, right? So 1 over gamma. First of all, do you agree that the problem is completely symmetric? So at the end, if we sum over all the logical links, we expect to have a factor of how many logical links we have? We have 10. 10 logical links over here, right? We forget about the asymmetries that are imposed due to the physical topology. In the logical topology, we calculated an average number, so we assume that for each circuit, this average number of, I don't know, path length or something, it corresponds to this, to all of them, right? We forget about the asymmetry of the physical topology. Now, over here, this will be equal to what? 10 times lambda ij for us will be the flow rate that we just flows per circuit. We have 10 circuits. The flows per circuit will be 3 gamma over 20, and in the denominator we will have, what is that? Is COC 38 is our service rate, the maximum capacity of the link, minus what it really flows in the link, which is 3 gamma over 20. And this gives why we have 10? Because of symmetry, right? Because all those terms over logical links are the same. So this will be 3 over 2 over OC 38 minus, we eliminate gamma basically from the numerator, and we have gamma in the denominator. So that's, you agree? Did you understand what we do over here? We calculated, we want to see the delay in the system. The question asks for, assuming uniform traffic matrix, find the network average delay. The network average delay for the two networks. this guy, we should think about this guy as being a network of systems or of queues. We have a service rate, we have an arrival rate. What is the arrival rate? Is the actual flow rate in the network. Okay, what is the service rate? Is the actual speed of the link. So we calculate the delay based on that. The more the speed of the link, the faster the system will be. Now, let's see. Yes, we have 10 logical systems. Each one of those is characterized by an average flow per circuit. We have 10 circuits. Each one is having its own average. All of them are characterized by the same average because it's an average, obviously. And that's what we do over here. We use basically this is Leeds law, if you think about it. This is the average lambda, capital, the queue length, the number of customers in the system, queuing theory-wise. Do you agree? Okay. All right, guys. So with that said, we can continue to the next topology. That's for topology number 1. All right. So for B, the physical topology in the second case will be the same, and we just have a difference in the logical topology we want to support, excuse me. So let's draw it again. This is a physical topology. And the logical will be, what do we want? For the logical topology, part B is fully connected mesh, obviously of 5 nodes. And in other words, we have a dedicated circuit between each source and destination. Make sense? Okay, so now let's quickly draw this. We have A, B, C, D, E. Now, good luck with that. Okay, let me okay, that's the ring. That's what we had so far, but now we have a logical link between every guy. So we need to continue doing the same for these guys. This guy needs to be connected here. Okay. We have internal lambdas. We have this link. Are we missing something? I think it's this one. Yep. That's it, right? Okay, so this is the logical topology or the virtual topology. And now you can think same way how we can implement this thing over this physical. And let's calculate the same metrics as in the previous example. Okay, so now we have total number of circuits here equals what? We have 10 plus 1, 2, 3, 4, 5. 5 times 2, 10. 10 plus 10, 20. Okay, so we have 20 circuits. That was given, but just to verify. Okay. The average circuit length in the logical topology measured in segments of physical topology equals to what? I would do the easy way, which is just count everything and divide by 20. I have 20 circuits. Let's see what's the length of each one of those. This guy, E to A is 1, A to B 1. Everything is 1. Do you agree? All these guys are 1 around. And then the reverse, A to E is how much? 4 segments. You have to go all the way around. We have to go in this network. We have to go A to E means A to B, C, D, and then E. So we have 4 segments. Those are segments, those are circuits. Each line over here. Do you agree? Okay. In other words, we have 1 plus 4 plus 1 plus 4 5 times. Okay, plus what? We have to find something for the internal guys now. We have another 10. We have, those are 10 factors over here, okay? We have another 10, which is the internals, which is, for example, from A to C, what is the length? 1, 2. No? Segment-wise. A to C. They are virtually connected, but the underlying physical topology has 2 segment hops. So A to C, or A to C is 2 hops, okay? And what is that? C to A is how much? 1, 2, 3. Okay. And the same, the opposite holds for this guy. So this guy, D to A, for example. D to A is connected 2, and then A to D is connected with 3. So all of those nodes, they have 2 plus 3 cost, or number of hops. So we have 2 plus 3, 2 plus 3, another 5 times. And this gives you how much? 50 over 20 equals 5 over 2. Do you agree? All right. So, what else? Now, we do the same analysis, number of circuits per segment. Is equal to number of circuits in total times average circuit length in segments and divided by 5, which is the total number of segments in the physical topology. And then this is equal to what? We have total number of circuits, 20. We just found the average circuit length, which is 5 over 2 over 5, and this gives you 10. All right? So now, to support, what does this mean? It means that to support this functionality, this connectivity over here, each physical segment will be the bandwidth of the physical segment will be divided by 10. Why is that? Because we want to support many links over here. All right? So now, with that said, maximum capacity per segment or per circuit. No, it's not per circuit, it's per circuit. Because per segment we know it's OC 192. Okay, so it's per segment. This is equal to OC 192 over what we just found over here, 10. And this is OC 19. Assuming everything exists, okay? All right, now, we want to do the same analysis for, this is part A again, this is part B. For the big A, and for the capital B part of the problem. And we want to do number of flows, that's what we calculated, right? Flows per circuit is equal to total flows over total number of circuits, and this is equal to, oh, no, I forgot something. I forgot to calculate some, what did we calculate earlier? We calculated the average path length. How much is the average path length in this graph? It's 1, right? Because everybody is connected to everybody else. So irrespective of where you want to go, the path length in hops, router hops of virtual topology is 1. So average path length equals 1 fully connected graph. Okay, and with that said, over here we have total flows times average path length excuse me guys, I messed it up. And this is equal to the external arrival rate as we did previously. Okay, just forget this term over here. I just do two substitutions at once. So gamma, which is the external arrival rate, times what? The average path length, which is 1, over the number of circuits, which is 20. Do you agree? Same as before. Okay. So now we can calculate expected T, same way, 1 over gamma, summation over all the logical links of lambda ij, and this is equal to 1 over gamma times 20 due to symmetry times what? What is our internal lambda? This over here, right? Gamma over 20, OC 19 minus gamma over 20. And this gives you 1 over OC 19 minus gamma over 20. That's your delay. Make sense? Any questions? It's exactly the same logic if you understand the first, second is just substitution. And yeah, just make sure you remember this approach here to find the delay. Okay, so let's go to the second one.
5-minute warning.
Thank you. The second one, we don't have time, obviously, because both are very long problems. I'm going to start it here, and we can continue if you want. We can discuss about it next Wednesday. We don't have a class over here. I'm going to be in the office hours. Okay? So there is no regular discussion, but we can talk about that. Make sense? Okay. So let's see the problem, and I'll sketch the solution. So the network shown is a simplified version of the California State RNE fiber network. Circles represent WDM multiplexers, and the lines between them represent a pair of fibers connecting them. This is the network, okay? The multiplexing equipment can support up to 2.5 gigabps lambdas. Okay, over here we can have 20 lambdas. There are 13 campuses that have to be connected, attached to these guys. Now, how they're connected? One is connected at Southern Santa Cruz, whatever is that, over here. Not Santa Cruz, it might be Sacramento. 3 at SY, 2 at San Francisco, 3 at LA, 1 at RV, I don't know what RV is, and 2 at San Diego. And the last one, EC. Okay? Each campus router must connect to one backbone router. 2 backbone routers are used, one in SY and the other in LA. One is over here and one is over here. 2 backbone routers. The backbone routers are to be connected in a ring topology over diverse fiber paths. So we want to support a ring topology over this physical topology for the backbone routers. So the backbone routers will be backbone router 1 and backbone router 2. Okay? So how the campuses connect to the routers and identify the most heavily loaded link in terms of waves. All right? We want to connect those campuses to the backbone routers and analyze what link is the most heavily loaded because of this logical topology that we want to support over this physical. Something similar to what we did. Assuming that the traffic to from each campus is 1 gigabps and that the traffic is uniform, compare the performance in terms of delay and traffic handling, performance characteristics of the design. Okay, now, for that, don't worry, we'll do a full solution. I'm not going to leave it like this. So just you can think about it and maybe discuss next time, or maybe we'll pose a solution. We'll see. How we should work in this case? We have, how many networks can we attach to LA? We want to connect, first of all, we have 13 campuses in total, and we want to connect them, some of them to one router and some of them to the northern router. The logical is to connect this guy and this guy's networks, campuses, to this backbone router. Okay? So this router will have SC belongs up here. SY belongs north, SF belongs to north. So 1, 5, 6 are connected to SY, and 7 are connected to LA. Or we can do the opposite. 3 to SF. We have 3 at LA, 3 here, 1 RV, 4, 2 San Diego, 6, and 1 at EC. So we have, I'm going to start and we'll do as much as we can, which I don't think it's much, but anyway. LA, we have a total of 7 campuses connected. So they give how much traffic? Why? Because we decide they are, geographically close. 7 times 1 gigabps. Make sense? Because we know that each campus is, assuming the traffic to from each campus is 1 gigabps. So the load in a LA router, we said that the campuses need to connect to one of the two backbone routers. Make sense? So the router needs to handle how much load? 7 times 1 gigabps, the BR1. So in SY, we have a total of 6 campuses.
Out of time.
We are almost done, guys.
For sure.
And this gives 6 gigabps. Okay? That's the traffic at backbone router 2. We'll continue the discussion. Let's stop here. We'll continue the discussion next time. Okay? Sounds good?
And that concludes EE 555 discussion on Wednesday, April 23rd, 2014.